Hello, my name is Al Leva. I am the Director of Product Management for Data Analytics Integration at BlackLynx, formerly known as Rift. The name of this video is Tableau powered by BlackLynx. Please feel free to email me with any questions at al.leva@blacklynx.tech. BlackLynx technology is focused on accelerating getting insights on your data. This is done with the use of high-performance heterogeneous computing accessed via standard applications and protocols in order to achieve high-performance analytics. The solution accelerates search-based analytics wrapped with easy-to-use and easy-to-interface to connectors, so applications like Tableau can make use of the OBC interface to access the power and features the BlackLynx solution has to offer. The details on the hardware, it's an x86, it's an FPGA, the data format, what computer server software is installed, whether it's in the cloud, is it on-prem or at the edge, are all really made transparent to the applications. Tableau users can focus on results to drive critical business decisions and don't have to be HPC experts. In this demo, we're going to connect Tableau Desktop, which is installed on my laptop, to the BlackLynx server via the ODBC connector. This will provide Tableau with access to search-based analytics that BlackLynx provides. Let me touch on these briefly from left to right. Things like exact search, Levenshtein, edit distance searching, fuzzy searching, time and date range, numerics, currency searches, IPv4, IPv6, regular expression searches, PCAP, protocol capture, binary file searches. In addition, and while not part of this particular demo, there are other analytics in our toolset for machine learning and deep learning. These include things like document similarity, engram analysis, image and video processing, and RF signal processing. In our demo, we're going to connect Tableau to an x86 FPGA accelerated server, but it could just as well have been a commodity x86 server or a server in the AWS cloud like an F1 or an i3. Or you could take a PCIe-based FPGA card, insert that into an x86 server, and our solution would automatically switch and select the primitives best used for the FPGA and the ones best used on the x86. It would do that seamlessly and automatically behind the scenes. Our goal in this demo is to show you some of the capabilities Tableau will access when using our BlackLynx technology. The very first one, the ability to search structured data without the need to ETL or index. And these include things like XML, JSON, and CSV data files. We'll have several examples with XML and CSV during the demo. We also enable searching of unstructured files, directly enabling Tableau to interface with these files as if these were of normal table format. Our technology allows for complex queries like fuzzy search and regular expression capabilities, both on structured and on unstructured files. These features are not native to SQL in general and not native to Tableau. We will demonstrate a few examples of those. In addition, we also enable Tableau with the capability to search and analyze raw PCAP. These are protocol capture binary files. These are especially useful for cyber, fraud, and threat analysis. We will walk through a few examples of those as well. In the end, our goal is to accelerate time to extract insights from the data, all without ETL or indexing of any kind. We're going to walk through some examples now. And let me exit presentation. And I have here a shell window that I just brought up. Now in this window, I'm going to run a small shell script. And the purpose is to display, run a shell script to display the information that we're going to be, that's loaded on our, is installed on our server that we're going to be using for the demos. The very first one is the Chicago crime data set, which came out of the Chicago crime records of arrests, of crime data that they keep in Chicago. This is about 1.4 gigabytes in size. And if you look at the very first record on there, as you can see, it's a typical XML file, right? So we're going to access that directly. Then you bring up a Tableau window. I have a window here where I previously created a dashboard, and it's going to go execute a query that searches the Chicago crime data with arrest. Therefore, all in the data set that contains arrest equal to true. And I render a nice visualization with that data set. So let me just briefly talk about what just occurred, right? We executed a search using Tableau, an SQL query for Chicago crime with arrest equal to true. And it takes that, sends it through SQL through our ODBC connector. The connector takes that information, converts that into the search primitives that BlackLynx utilizes. We search the XML data set directly, and then return those results to the connector, which then takes those and converts that into a format that an SQL engine typically expects to see. In this case, and look at data source here, and then in the data source you can tell has a typical tabular format. It looks like a normal table, but as we saw from the file, it's really an XML data set. Let's go ahead and run through another query. I'm going to bring up another window, and we're going to execute some SQL queries directly. Okay. So let's connect to the server. Okay. Okay, let's talk about this for a second. We're going to execute again on the same data set, Chicago crime, and we're searching for description containing electronic and block containing Indiana. Now, you'll note that these are wildcards specify the beginning and ending of each one of those terms that's being searched. Now, we don't know where in the column that data is located. It could be left justified, or it could be right justified, or somewhere else. In a typical SQL search with indexes, if it's at the beginning of the column, then it's fairly straightforward, right? But in this scenario, where we don't know, it would require first creating 10 tables and then walking through every one of those records. And that, of course, can be time consuming. Using our compute technology, we look at every byte all the time. So it doesn't matter to us if it's left justified or right justified, since we look, or somewhere else for that matter, since we look at every byte all the time. Let's go ahead and execute this. Okay, so here's a block, and here's description, and you can see Indiana is somewhere not left nor right justified, somewhere in the middle, and description has electronics, so again somewhere in the middle of the record. So we just demonstrated the power of being able to quickly search every byte and not having to lay out indices based on where the data is located. Let's go ahead and execute another search. Okay, now in this case, we're going to be executing a fuzzy search with an edit distance of 2. So what's an edit distance? Well, edit distance is fuzziness. Fuzziness is really is measured as a number of insertions, deletions, or replacements required in a particular term that you're searching to declare a match. In this case, we're doing an edit distance of 2, right? This is also known as Levenshtein edit distance search. And so what's 2 mean? So 2 means I could have up to 0, 1, or 2 characters either edited, either deleted, added, or modified to make this term equal to true, right? But as you can see from Tableau, typically a fuzzy search is not something you can normally do. You can't do that normally in SQL, right? But we do that, enable that through a simple extension to the SQL syntax, right, with E-E2. This type of query is typically hard to do with standard SQL. you have to do a dictionary of some kind, right? And it would contain a list with all the different spelling variations for Michelle Jones in this case, right? Which assumes, of course, that all variations can be captured. But more importantly, it would not really work very well if someone was purposely trying to hide the name by inserting characters in somewhere, right? And you don't know how many characters or which characters. Let's execute it. It's best described when execute it. So let me do that. So here's a variation. It's Michelle Jones spell, right? There's several examples. Here's the exact term, Michelle Jones. Here's Michelle Jones um, uh, with an S inserted, distance of 1, so one character was added, right? Here's Michelle Jones with an L removed, so a character was removed, right? Here's a Michelle Jones with an S replacing a C, so a character was updated. So those are examples of edit distance of 2. Now, fuzzy search is not new, right? But typically, most applications are so slow executing fuzzy searches that they're typically not done. But with BlackLynx technology, the power of solutions allows us to execute these complex queries very, very fast. Let's go ahead and execute another search. Okay. Okay, so in this case, we're going to take a look at log files. It's about 21 gigabytes of data. Like fuzzy search, this is another search not typically available in SQL. In this case, it's a regular expression search denoted by the -R here, right? Um, in this case, we're looking for an IP address, right? But we don't know specifically what IP address. Quite the opposite is true. What we do know is that what IP address we want to exclude, basically all the 172.31 subnets in this scenario. These types of searches can be challenging for relational database and index-based systems. Typically these indices works well when you know what you're looking for, but the power of regular expression lets you search for the negative assertion, right? Oh, in our case, right, we want to look for the list of the IP address records that don't have the 172.31 in it. Let's go ahead and execute this. And while that's doing, let me just quickly go with this table here, the file here. So here is the log file. Um, it's 21 gigabytes in size. Typical log file, right? Here's the first record in that log file. In this case, that record contains the IP address we don't want, 172.31 subnet being in there, right? So let me go back and let's take a look at the results. So let's see here. So here's matches, right? All these that match are not in the 172.31 subnet, which is what we were requesting, a regular expression search. But you'll notice a few other things that are returned. Now, one of the things I didn't mention in the query, and if you look at it one more time, there is a width parameter, a surrounding width criteria, width of 20. What does that mean, width of 20? Well, since this is a log file, right, it's not a structured data. And you just saw Tableau execute a search on unstructured data. And width of 20 says, whenever you find a match, give me surrounding text. What's 20 characters past the match and 20 characters before the match? That gives you some context, right, as to what was around, what was happening, what was being logged at that time, right? So that's what that's about. So I got some surrounding text around that match, before and after. We also, in addition, have the log file, the specific file that contained that data. Had there been more than one file, obviously it could be different log files matching that criteria. And one other thing, right? You have a couple other things, excuse me. The offset, the exact position, right? Results, the detail, the pointer, basically use it as a pointer to match the location in that log file that contained that match, and then the length of the data that was captured, right? So you just saw Tableau execute a search on unstructured data and return information that could be useful in doing some further analysis. Let's go ahead and execute another example. Okay. So in this case, we're not looking at logs, but they say some other documents of unstructured text of some kind. It happens to be Wikipedia, um, and we're going to be executing what is known as another regular expression example, right? And is known as a proximity search. Um, so what exactly is a proximity search? Well, um, you have the word beautiful and the the word world are approximately close to each other. Well, how close? Well, 0 to 5. That means I could have 0 to 5 words in between beautiful and world. That's a proximity search. And again, I'm doing a surrounding width of 20. You could choose another number. I chose 20 to give you some context. So let's go ahead and execute that. And let me, while that executes, bring up the file here again. So let's look at that. So that data set here is a 22 gigabytes in size. It happens to be the Wikipedia English version that we downloaded. And here's an example of some records in the data set. And you can tell it's kind of an unstructured, no, or semi-structured, more accurately, where it contains some XML, what looks like maybe some JSON, and maybe some hypertext as well. So it's a mixed bag. So we're treating it as an unstructured text. So let's go see what these results look like. Okay, so here's the search, and it's beautiful and world with 1, 2, 3, 4 words in between, right? Here's another example, beautiful and world with 3 words in between. And known here somewhere, oh, here's beautiful world exactly, right? Beautiful world with 0 words in between, right? And of course, like the previous regular expression search on the unstructured file, the unstructured log file, here the same thing here. You have the file that contained the match, the offset position, character position where that match was found, and the number of characters contained in the length of the data that matched it. Okay, let's go ahead and execute another example because we just demonstrated in this case the ability to Tableau to execute the power of regular expression and fuzzy searches by simply connecting Tableau desktop to the BlackLynx server through the OBC connector without any changes whatsoever in the Tableau client. That's a very important note. Let's go ahead and do another search. Okay, so in this case, we're looking at CDR or call detail records, right? And we're searching the mobile station international subscriber directory number. Now, in this scenario, we don't know the country code and we don't know the national destination code, which characterizes the subscriber operator. So all we know is the subscriber number directly, 951,354. We know that, but nothing else before it. So wildcards are used in this case. Let's go ahead and execute that. And I'll bring up, let me do that. And let's show the shell window momentarily. Let's take a look at that record. So here's the call detail records. Now, this happens to be 65 gigabytes in size. And you'll note this one is a CSV format, right? Let's go back to here. And let's go look for MSISDN, results return. Here we are. So here's MSISDN. If I could remind you of that, right? So we search for 951,354 and then wildcards, and you notice the differences in there. Now, as a side note, the customer had used Elasticsearch cluster to do this, and while the data is in indexed, the indexes work really well with trailing wildcards, but not leading wildcards. So in our case, we can use the power of BlackLynx solution with Tableau to query the query on the CSV file without any ETL or indexing of any kind, using, in this case, leading wildcards. Let's go ahead and do another example. Oops, let me get that. remove. Okay, now in this scenario, we're going to do another regular expression search. In this case, it's a little bit different. We're going to do it on PCAP, a protocol captured binary file. And we're searching for an IP destination containing this particular IP address and the payload containing a regular expression with some kind of serial number, 56169 and 4 digits. If you're familiar with T-Shark and tools like T-Shark and Wireshark, very similar. You do filters in T-Shark and Wireshark to do this kind of thing. But this kind of feature is not typically done by SQL engine, certainly not typically done by Tableau. Let me go ahead and execute this. When that's running, let me bring up the window a second. So let me show you that. So it's a PCAP files, and there are 15, 16 or so files in here. They're about 16 gigabytes in size, in total size, and there's the whole list of files. So we're going to search. We're searching them all at once, right? So let's go take a look at that data set. All right, so here's results returned. And if you're doing PCAP today, you're probably using tools like T-Shark or Wireshark, right? And to actually filter down the PCAP to the IP address, like in our particular example, right? I mean, look at the payload. We're talking about this. Here's the payload with the 56169 matches that we were looking for, and different numbers in there. Now, in tests that we run using T-Shark, it takes about 23 minutes with a 22-core machine to filter down a 1 gigabyte file, like we just did. We have 16 gigabytes in our example, right? If you remember here, 16 gigabytes. So using T-Shark to do that same kind of thing, it would take about 5 hours or so. And you have not yet looked at the payload that we just did. That's just filtering on the IP address. Another approach perhaps you can do is also use again T-Shark, but only to decode only, right? No filter, and put the output to a JSON file, and then search that. That will work, of course, but now imagine the original 1 gigabit gigabyte binary file, PCAP file has now grown to with 40 gigabytes in size for one file, which is in JSON format. So in our example, that would be over 600 gigabytes in total size to search in JSON. Let me do one more example with PCAP. Okay, we're going to do the PCAP again. This will be our last example. Again, we're looking for an IP address. This is an IP destination address. Oh, I'm sorry, this is the wrong example. Let me cut that one out. That's the wrong one. I apologize. That's the example we just ran. So let me do another. Okay, this is what I want to run now. So we're doing, in this case, we're selecting IP source, destination, and HTTP request URI, again from the same PCAP data set. We're looking for an IP destination of this, but we're looking for HTTP request method. So anything that had that IP destination and the HTTP request method of GET. So let's go ahead and execute that. And so these, again, are the same, similar results. The IP destination, and this is request URI that requested to be displayed for all the HTTP request methods of GET. Okay, so I've just demonstrated running fast, complex queries with fuzzy search and regular expressions on structured and unstructured data, all without ETL or indexing. At the end of the day, with the power of Tableau, we can render dashboards with visualizations. Now, I'm not a visualization expert, but here's a few that I had done earlier. Here's another dashboard that I had set up. This is a PCAP, right, dashboard that I use with very nice visualizations that Tableau provides. Here's one with Bro logs, the blower logs dashboard that I created using Tableau as well. Um, and this happens to be a TSV file, tab separated value. Then there is the NetFlow dashboard, uh, another tool for analyzing network traffic. Again, another nice visualization that's been rendered by Tableau. So to wrap up the presentation, let me go back to the presentation material momentarily. Okay. I certainly hope that I was able to convey to you, the power of BlackLynx solution coupled with Tableau brings, right? Uh, Tab BlackLynx and Tableau technology working together to supercharge the speed and capabilities of the analytics, and bring them features like, be able to do PCAP and network forensic analysis, to execute uh, regular expression searches on structured and unstructured files, right? To execute complex queries with Fuzzy Hamming and Levenshtein edit distance searches. And all that, they're reducing or eliminating ETL or indexing um, on that data set, whether that data set be XML or JSON or CSV. So Tableau is thereby empowered by BlackLynx to accelerate the time to extract the insights from your data to really near real-time performance. So I thank you for attending this video and listening to my presentation. And again, if you need some additional questions, please contact us at support@blacklynx.tech, or you can email me directly at al.leva@blacklynx.tech. Thank you.